And as I believe Courtney might have announced in the last, she has moved on with a little career change. She's gone back to high school as a guidance counselor and campus minister at Sacred Heart Griffin High School here in Springfield. So you all get me for the near future and may be joined by our new colleague Ariana Antonacci as well over the coming months for the First Friday webinars. So with that, there are a couple of changes and announcements I want to make as we move forward. We've established a link on our website for the quizzes. So as you start to register for these First Fridays from now on, you should receive within 24 or 48 hours of registering through the ISP site the registration link for the GoToWebinar. So you won't necessarily need to wait until the day before, 2 days before to get that email. That will allow you to get that information. We will upload the quiz link when it's ready to that site, and you'll be set to go. Also, one other little change is that we have uploaded the handouts to the GoToWebinar screen. So on the right-hand side, you should be able to see the handouts listed there for you to download. So the handouts are there. If you have any trouble with that, feel free to contact me after the webinar and we can make sure you get those to you. Again, the P8 certificates will be emailed to you within the next couple of weeks. Please take the quiz no later than 8 a.m. on Monday, and we will get those quizzes graded this time we'll give you till Tuesday. We'll get those quizzes that have come in graded and try to expedite the process of getting those certificates to you in a timely manner. Let me see what else we have here. Oh, one of the other things that we're going to do, and I'll launch this toward the end, is a poll just to measure. I know that some of you were planning on broadcasting this to several people in your office who didn't necessarily register just for information purposes. So I have a quick poll that I'll do toward the end to see how many were watching with you in your office, just so we have an idea of how many total participants we have. So without much further ado, I am going to hand things off. We are very fortunate to have with us Joel Graff, PE, from the Illinois Department of Transportation. And he is going to be talking about integrating 3D CAD modeling using the Bentley MicroStation into transportation engineering at IDOT. I'll turn things over to Joel.
All right, thanks, Suzanne. As Suzanne said, we're talking about integrating 3D CAD into our engineering workflows here at IDOT. I am among right now one of 3 people within IDOT who really are understanding what exactly that involves. So it's a long, slow process, both to this point where we are now and to where it's going to be something fully integrated and just a part of the way we do engineering on a day-to-day basis. We are, as Suzanne said, working with Bentley MicroStation, and right now, if you're a shop that uses Autodesk products to work on state contracts in the future, hopefully somebody will find a way to translate 3D modeling from Autodesk's, for example, Civil 3D to Bentley. If not, there will be the need for our consultants then to be able to provide those models in using Bentley's formats. So that's just sort of a heads up for those of you that are interested in working on state contracts in terms of 3D modeling. So to get started, hang on a second here. There we go. So to get started, we're going to explore 3 key questions as we go through this presentation. Number 1, why at IDOT are we doing this? Number 2, how does this work? And we're going to talk about 3 different areas in which 3D modeling applies. Number 1 is construction. Number 2, visualization, which is more preliminary engineering. And number 3 is design. And finally, we'll briefly look at what it's actually going to take to get there from where we are right now. When we talk about why we're doing this, there's an executive leadership commitment that states that IDOT wants to implement 3D engineered modeling from project conception and initiation through maintenance and operation. Notice the scope of that statement: project conception and initiation through maintenance and operations. In IDOT, traditionally, project lifecycle consists of 4 key phases. Phase 1, preliminary engineering. Phase 2, design. Phase 3, construction. And phase 4, maintenance. So your project lifecycle then actually, most people don't even think of maintenance, but project lifecycle actually continues through that. And this 3D model will begin then in our preliminary engineering and be useful in public meetings, through design, in construction, and in developing and engineering the final product, in construction and building, and then finally in maintenance, where we're going to be being able to track significant changes, things that we do to the roadway in our maintenance cycle, so that when the next project that goes through there needs to know what's been done in the intervening time since the end of the previous construction and the start of the next project, they will have that 3D model which describes all of the maintenance activities which have occurred in that time. But the real primary reason why we're doing this, at least now, is because contractors, general contractors over the years, more recently, have incorporated higher technology into their construction equipment, to the effect that the equipment is now GPS enabled. And with the ability to program in 3D coordinates into their construction equipment, they can establish grades quickly and efficiently. And as a result, the general contractors have kind of lobbied the FHWA to get the DOTs on board with this 3D engineering. And so as a result, the FHWA has mandated nationwide all DOTs must implement 3D CAD into their engineering workflows. So every DOT is dealing with this on some level or another. Some have fully integrated. I think Iowa and Minnesota maybe are a couple that have. Michigan, I don't recall. And some are at various points along the process. Some have only barely begun. Well, how does 3D modeling work then? What exactly is this process, and how does it actually work for us in an engineering context? Well, it's important to distinguish the 3D modeling we're doing in this context. In order to really understand the value of it, we need to talk about how we do engineering right now in CAD. And our current processes are focused on two-dimensional 2D CAD processes. And so in the end, what we're doing is we're creating a model of reality. In fact, everything we do at IDOT pretty much is all about modeling reality somehow. And right now, using our 2D CAD processes, in order to create a model of the finished product, we actually have to create 3 distinct models. Generally speaking, they're the top, side, and front views. For any of us who are familiar with CAD, that's a pretty familiar terminology. In the industry, we call them plan, profile, and cross-section. In a 3D model, we're building one and only one model. And this model is parametric and volumetric, and we'll talk about what that means in just a little bit. This is a model that everybody uses across all phases. It's one and only one model that everybody has access to. And finally, those 2D views that we live and die on right now really become just a secondary consideration and can be arbitrarily generated at any point in the life cycle. So when we talk about this new 3D modeling, it's important to understand that what we're talking about is actually parametric modeling and not 3D modeling in the traditional sense. 3D modeling in the traditional sense is all about building meshes, points interconnected by edges that generate surfaces. If you take a look at the background graphic there on the right, you see a lamppost. It's an asset that I created for something we'll see in just a little bit. And you see the wireframe mesh that lies behind that surface. In traditional 3D modeling, ergo the sort of thing you'd see at, say, Pixar when they make a movie, they are focused on working with that mesh directly, pushing and pulling vertices to change the shape of that surface. That is a very complex and detailed way of dealing with 3D modeling. It's something people go to school for exclusively to do, and to try to back end that on engineers trying to build highway models just isn't going to work. Parametric modeling sidesteps that whole issue and allows us to express or design our 3D models in terms of engineering parameters and constraints. And as a result, once we've specified those parameters and constraints, the software then generates our 3D model for us based upon those specifications. It's a much more powerful, straightforward way of doing it. But in the end, the workflow to actually build something in 3D is entirely different, completely different from doing something in 2D. I might liken it saying is moving from Windows to Mac, but I can't even say that the comparison is even that similar. I think it's even more different than that. And so the mental shift that's required to think in terms of a 3D parametric modeling versus our traditional 2D processes is really substantial, and it's really a major hurdle. So in terms of construction, ideal applications for 3D modeling are primarily new construction and reconstruction projects where you're undergoing major profile and or cross slope changes, okay? Again, in terms of construction, there's little or no benefit for projects where you have narrow surface widenings, mill and fills, overlays where you have little or no profile or cross slope changes, locations where you have poor GPS signal. And I'm not talking about the boonies in the middle, not only talking about the boonies in the middle of nowhere, but also urban environments where you have large buildings that might occlude that signal. That makes 3D models less valuable than in terms of construction. Also locations where there's little or no existing survey. That is becoming less and less of an issue these days as it used to be with the proliferation of LiDAR data, for example. If I'm right, for example, the state of Indiana has produced, put online LiDAR data for the entire state to varying qualities and degrees. So the proliferation of survey data is becoming less and less of an issue, but it's still a problem out there. Actual benefits that we see on the ground in construction. Number one, the goal is to have a 3D model that is fully constructible. The idea is that once a 3D model is published from design to the construction phase, that model will contain anything and everything required to fully construct that project. The ability to stake anywhere within the project limits is entirely possible. The entire project, every point in that entire project is defined, and so every point can then be staked. We have improved accuracy in transitions, intersections, and earthwork. That's especially important because right now, contractors who wish to produce 3D modeling or produce 3D models from a 2D project, they can do that. They can take a paper set of plans from a DOT job or something, and they can produce a 3D model from that, but the software that does it, it doesn't generate very good accuracy where you have funny stuff going on, you know, or transitions from a side road to a main line or tapers or things like that. It works best where you've got long, straight, generally unchanging sections of roadway. This, of course, being a native 3D model from the start will eliminate those sorts of inaccuracy issues. Utility conflict identification utility conflict identification is greatly enhanced with the caveat of garbage in, garbage out. At IDOT, we are a member of Julie, and we rely on the accuracy of the utility owners who are also a part of Julie to provide us that information. We are not saying with 3D CAD that the location of the existing utilities is any more accurate than it was in the past, since we don't have control over that. But what we are saying is that assuming that utility location information is accurate, we can very quickly and very easily identify where, say, for example, a storm sewer gets too close to a water main or a ditch cuts into a fiber optic line. Another major advantage is that changes are propagated to everybody. And what I mean by that is that if, you know, in design or in construction we realize, oops, somebody forgot a turn lane, they can call it the designer. Designer can make those changes implemented into the model, and as soon as they push go, as soon as the changes are pushed to the model, anybody who has access to the model anywhere within you know, in any phase of the process, we'll see those changes immediately. There's no need to figure out who is responsible for what, who needs copies of what, and produce 2D copies, you know, of plan views and cross sections and profiles and that sort of thing. Everybody has access immediately. Another major advantage, and we've experienced this directly, our own District 9 down at the bottom of the state has produced a few 3D models, 3D CAD projects for construction, and we've experienced up to a 50% increase in staking. Reduced manpower and faster staking is major advantage to this. But the real value to it in the perspective that I have on this is not so much how it helps construction. That's well established, and that's been proven in practice. The real value is figuring out how it's going to help us in the preliminary and design phases of a contract project. And so I want to take a moment and focus then on visualization. And visualization is really all about preliminary engineering. It's not a part of the IDOT roadmap right now, but it's going to very quickly become a part. It's going to be a very valuable addition to the process of developing a highway engineering project. When we talk about visualization, what we're doing is we're producing an existing model of a location that's going to see an improvement, and merging that with the proposed improvement. Okay, we've seen this done all sorts of times. We've seen the color, you know, the color printouts of, say, a river and a picture of the proposed bridge pasted on top and things like that. But in a 3D sense, when we produce a 3D model for visualization for preliminary engineering, we are able to increase the amount of information that we can communicate with a single model 50 to 100 times over the amount of information you can communicate with simple two-dimensional pictures or plan and profile views and cross sections. Because you're really asking a lot when you take this stuff, especially to stakeholders and public meetings and local officials, to ask them to look at these two-dimensional engineered drawings and abstract in their minds the proposed 3D model that, you know, we may intuitively see as engineers. And by producing that 3D model, everybody intuitively understands 3 dimensions. Everybody intuitively, you know, we are 3-dimensional creatures, and we can very easily extrapolate, you know, the end result from the 3D model. Another advantage to this is that they can be interactive. And when I say interactive, what I mean is they can be anything from a pre-programmed fly-through going down the road or along a path to a model where the user can actually navigate themselves through it. And the other advantage, at least on an internal side, is it allows us to rapidly prototype solutions early on to see how they look, how they impact the environment, and what sorts of challenges any one given solution may provide in the course of doing the design engineering. So when we talk about prototyping and building a visualization, a preliminary engineering model, we need first to reproduce the existing infrastructure, and that's done primarily one of 3 ways. Number one, we can grab existing LiDAR data. It's a tool that's out there that everybody knows and uses a lot. A second is laser scanners, and if you're not familiar with laser scanners, excuse me, if you're not familiar with laser scanners, they look like total stations, like your regular survey instrument. You set them up on a street corner, you push a button, and they literally scan their environment, producing what's called a point cloud of data. If you look at the picture on your right, that's actually, it looks like a dense contour map where you can see, you know, the sidewalk, the street, the back of the stop sign, the facade of the building. You can even see the power lines. Those are actually individual points, so dense they look like contours, produced by a laser scanner. Once we've developed that point cloud, we can bring it into a software. We can produce a mesh, which creates a solid 3D surface, and reproduce a very, very accurate existing model quickly and easily of our existing conditions. The other method that you can use is called photogrammetry, and that's more of a manual method. I've actually done this with a church in a 3D modeling software. Somebody gave me 4 low-quality iPhone pictures of the inside of a church, and I built a reasonably accurate 3D model of the entire thing just from those 4 pictures. That technique gets used a lot, even in MicroStation CAD, for producing unique 3D elements or maybe quickly producing a visualization of something where we don't have access to more accurate information. Then after we've gotten our existing infrastructure, then we start integrating 3D prototypes with that existing infrastructure. We're not talking about pasting or superimposing, you know, like we typically do in our 2D pictures of bridges crossing rivers. We're talking about taking a real 3D model, 2 3D models, and merging them together. And with that final visualization done, then you can explore how those models fit and what sorts of impacts they have with each other from nearly any vantage point and any angle. And finally, having produced that visualization, we can deliver it on a multitude of platforms. We can 3D print it. We can produce desktop or mobile simulations. We can do virtual reality with an HTC Vive or Oculus Rift or, I don't know, Google Cardboard if you want. We can deploy it on the web, and people can log in through a web browser and actually look at this 3D model through the web. So there's really a variety of ways of being able to get this model out to the public or to the stakeholders. So I want to take a moment and show you what a visualization like this actually looks like. When I got involved with 3D CAD, one of the first things they asked me to do was to play around with this project that we're working on. And the project is Route 2 from Byron to Rockford. If you're familiar at all with that area of Illinois, a few years ago we rebuilt Illinois 2 from Oregon to Byron. And we reconstructed the entire pavement, built new PCC, widened it, just did a beautiful job. It's fantastically better to drive now than it was before. Now we're going to do the same thing from Route 2 from Byron to Rockford. And the picture you see in front of you is a railroad overpass on Route 2 just as you're heading out of Byron. And then there's a little pull-off on the right. And when I got involved in this, I have a history of doing 3D modeling and things like that and visualization. And the people that got me involved here at IDOT said, can you do a before and after of this location, of the bridge? Because we want to add a multi-use path and, and widen the road and things like that. Can you show what it would look like before and after? And I said, well, we can try. And so I set out to do that just to see what you could do to build a visualization. And I never built the after, but I did build the before. And I kind of want to show you what that looks like. Here we go. What you're seeing here is a 3D view, a 3D model of that existing surrounding. And what I did was I built it using IDOT LiDAR data. I used a 3D modeling software. It's open source and free. Anybody can download and use it. It's called Blender 3D to build the models. And then I incorporated it into a gaming engine called Unity 3D. Now Unity 3D, you can download and use that for free as well. If anybody out there still plays games, I do. I'm kind of into that sort of thing. Most any video game, mobile or desktop anymore, is built in Unity 3D, but it's also a great general 3D visualization environment. So in the course of a month, because I was just kind of working out the bugs of how these things work, I managed to actually build this environment in 3D, and I can run around. I mean, if we wanted to, we could drop in some guns and ammo and health and have a frag fest in here. Might not be a real interesting, but you can run around and you can maneuver in this like you could any 3D game. And one of the things I did was I went out and I actually took pictures of the location. For example, here's a farmer's market sign that's out there in the pull-off, and I used it directly to build the 3D models. And if you get up close, you can even see that the letters look like they're actually carved into the wood. You don't normally want that level of detail in a visualization, especially for preliminary engineering, but it just goes to show you how powerful these visualization engines can be if you really want to put them to good use. I provided a general grass texture for the grass. Unity 3D has speed trees. It's an algorithm that generates fairly realistic looking trees of whatever type and size and shape that you want. So I was able to reproduce those, and those kind of represent what's actually out there. Parking blocks and the pull-off. The ground, the pull-off, the roadway, all of that, like I say, was pulled directly from IDOT LiDAR data. Over here we have a pavilion, which I used photogrammetry. I used pictures I took from the ground and Google aerial photos to build that. I didn't actually take any measurements whatsoever. It turned out fairly well. If you come over here and take a look at the path that goes from the parking area, there's a couple lampposts as it is in the real world. Here's a picture of that lamppost, which I used, and I used this picture directly in Blender 3D to build the actual model. You see that the lamp itself looks kind of gray and clayish. That's because I never actually finished texturing it or applying materials to it. There's kind of a chip paint look on it. I could have done it. Wasn't really worth the time. If I wanted to, I could actually activate those sconces and make them light things up. We could make this a nighttime scene, and you could see how these existing lights light up the path and compare it to, say, a proposed lighting scheme. We could throw in some proposed lights and show how that difference looks and compare them directly. If you move up on the berm here, up onto the railroad tracks, I managed to reproduce the actual railroad tracks with the ties and ballast. We can come to the end, and we can see here the LiDAR data ends because the bridge picks up and takes us across the Rock River. And if we go back the other way, we'll just run down the tracks here. We can come up on the overpass, the Exelon overpass itself. And I took the time just to mess around. I took the time and actually modeled the cable bridge railing on it. Now, this is not something that could be very easily done. I don't know if it could be done at all, really, in CAD as it stands. So this is something I had used Blender to do, but I was able to reproduce fairly accurately the cable stays or the cable railing there on the bridge, just to see what it could be done. But if you jump down and take a look at the bridge itself, what I did was I went out and I took pictures of it, and I got some good close-up photos of the bridge beam, or the facing beam. And this is an old Carnegie beam bridge from the 1930s. So we had the as-builts. I was able to get the beam sections easily online, so it was really easy reproducing that bridge. And then I went out and I took the pictures, and what you see on that beam are those pictures that I pasted together in an open source photo editor, much like Photoshop. And then I brought it into Unity, and you can see it produces a pretty realistic reproduction. So overall, I should also mention that one of the other nice benefits to using this technique was I was able to incorporate these floating billboards. So obviously in the course of a public meeting, you'd be able to say, you know, put up information that would explain to the stakeholders, this is why we did this here, this is why this retaining wall is here, this is why the road narrows here, et cetera, and explain to stakeholders what the engineering processes and problems were as we were working out this design. So overall, I feel like this is going to be a very valuable sort of element that is going to become a part of engineering, preliminary engineering in the future, probably sooner than we think. But at the time, like I say, it's not really part of IDOT's roadmap. So moving on though, when we talk about it in the context of Bentley, I used free and open source software with the exception of Unity 3D. It's free, but it's not open source, it is licensed. But in terms of doing it in the context of Bentley MicroStation, Bentley acquired a company that produces a software called LumenRT. And LumenRT is a lot like Unity 3D. It's not as capable, if you ask me, but it is set up to accommodate civil engineering purposes, and it's certainly much easier and faster to work with. And it allows you to produce really good looking real-time visualizations of a finished product. So for those of us working with Bentley, if and when we get into visualization, LumenRT is going to be the way we'll want to go. But visualization has its uses right now, even in the design phase, even if we're not producing, you know, games or fly-throughs or walkthroughs or whatever. In fact, I've already used it just in 3D CAD to help us determine the impact of changes we want to make. And a good example is Lake Louise along Illinois Route 2, just north of Byron. There's a trailer park on the opposite side, and then there's an access road that fronts Lake Louise. You can see both there in the picture. And both of them created some interesting challenges for us that we're trying to work out in the preliminary engineering phase. First, the trailer park. Excuse me. The trailer park itself is really close, and actually let me go back. The trailer park itself is quite close to Route 2, and you can see in the lower picture on North River Drive where the near the entrance, near the intersection rather, there's an entrance into the trailer park, and by policy that's too close to the intersection, so we have to shut off that entrance. So we want to improve the rear entrance and provide a better road inside the trailer park. But the question that came up was, that trailer on the very end closest to North River Drive, are we going to have to get rid of it? The assumption was, yeah, we probably will. But the question came up and I said, you know, let's see if we can use 3D modeling to figure that out. So what I did was I was able to reproduce the existing roadway inside the trailer park, which is that slightly darker gray that you see throughout the picture there. Surveys provided us the footprints of all of the buildings in the area, so I was able to provide a quick mock-up of just a box shape that followed those footprints to give us a pretty realistic idea of how the trailers laid out in there. And then our geometric staff provided me with a geometric alignment for the proposed roadway. So I laid that in there, and I ran out a template, which we'll talk about in just a second, and that gave me a clear picture of how the proposed roadway might look inside this trailer park. And that's what you see outlined there in the blue and the orange within the trailer park. And the consensus in the end was that if we play it right and we're careful about it, we probably don't have to move that trailer. So this took me probably a couple weeks to work through because I'd never done it before, but you know, it might represent a few days worth of work now. And in my mind, you know, even a few days worth of work just focusing on that is probably worth it just to determine answers to questions like that. On the other side of the road is the Lake Louise access road. And this was kind of an interesting challenge because what we want to do is put a multi-use path alongside Route 2 from Byron all the way up to Lake Louise. Now, in reality, we're not actually going to put the path in because we can't find people we can't convince the local jurisdictions to take responsibility for it. But we were thinking maybe we could at least put in the embankment. So the question was, that access road along Lake Louise, is it in, you know, do we encroach on that with our multi-use path? And the real problem in solving this was that while I had LiDAR data for the Lake Louise area, I didn't have any survey data which told me where the road was. So in order to solve that, I took our 3D terrain and I laid this aerial photo over top of it, and then I simply drew in a center line along the access road, which you can see on the left-hand side there. I faked in a center line basically along the access road that looked pretty good, and I used that to build the model. Now, is it accurate? Yeah, I don't know. If you're okay with an error, you know, of maybe 1 to 2 feet, yeah, it's reasonably accurate. Is it accurate enough for what we're trying to do? Absolutely. And it gives us a picture real quick that tells us that, yes, in fact, our embankment is very likely going to impact that access road right where it's along the front edge of the lake. So there's no moving the access road. We're going to have to do something about our embankment. And again, this took me about a week to do, 3 or 4 days. This would be, you know, a day or maybe half a day for somebody who's really experienced at it. So moving on then from preliminary engineering, how then does 3D CAD work in design modeling? And this is where the rubber really meets the road for us. When we talk about design modeling, there's 3 major advantages to using 3D engineering. Excuse me a second. There's 3 major advantages to using 3D modeling in design engineering. First off, it's real time. If we make any changes to our alignment or profile, the model automatically updates to show us what our cuts and fills are going to be throughout the entire section. Second, it's volumetric. We are producing a 3D model with actual volumes, pavement thicknesses, and widths and everything as it's intended to be built. That means we can automatically estimate quantities from it. Number 3, it's parametric. It allows us to incorporate our existing engineering practices into the design process. We're not building or working with the mesh directly. We're simply saying, I want my road to be 12 feet wide. I want my cross slope to be 1.5%. You know, I want my radius to be 30 feet, et cetera, et cetera, et cetera. And the software is then taking those engineering constraints and building a 3D model for us. So in order to begin a design modeling project, we need first to generate an existing terrain model from our survey data, which is something we're already doing. We need to create our alignments. Now, traditionally, we do that in GeoPack, and then we bring it into MicroStation. GeoPack is going to die. And right now, in the SSE4 edition of Power GeoPack or MicroStation Open Roads, excuse me, the software has now incorporated new vertical geometry tools to replace what's in GeoPack. The Kobo geometry system and all of that stuff, it's gone. Everything is now done inside a single DGM file. You know, and a lot of the referencing that we've had to do in the past just doesn't happen anymore. We construct our model using 2 primary 3D tools, roadway templates and civil cells, and we're going to focus on those for the rest of this presentation. And finally, our model is generated excuse me, our model is generated using feature definitions. A feature definition is simply a technique in which in the 3D model we can distinguish between, say, an asphalt surface, you know, and a concrete shoulder, or, you know, a turf buffer and a concrete sidewalk or whatever. And so those feature definitions are really, really critical to the whole 3D modeling process. Roadway templates. When we talk about a roadway template, we are talking about something that is almost exactly analogous to a typical section or a cross section. Better to think of it in terms of a typical section. For example, you see in front of you a roadway template for an urban section with 4 lanes and a raised median in the center. It's got curb and gutter and sidewalk on either side. All those yellow lines with the red pluses on either side are what are called end conditions for the fill or cut, depending on whether the road is above or below the profile grade. You see, for example, the yellow lines that extend downward, those are fill slopes. There's 4 of those. And then the yellow lines that extend upwards, there's actually a ditch section behind the sidewalk to accommodate that. And then upward slopes depending upon, again, how far above or below profile grade the roadway runs. This single roadway template, if we were to produce a typical section for all of the conditions that this roadway template addresses, it would take 64 typical sections to accommodate all the combinations of fill and cut slopes and whatever else, all right? So a single roadway template is a fairly powerful tool. It's a fairly powerful way to express what's going on at any given point throughout our project. This is a quick example of what a roadway template can do for us. The roadway, this is again a part of Illinois 2 from Byron to Rockford. It's 10 miles long. There's probably 3 key templates that I started with to build out this initial model. And in the course of maybe 2 hours, I can generate a 3D model of 10 miles of resurfacing and reconstruction. If I've got a good alignment and I've got the templates I need, it'd take probably a couple hours to build something like this. So in the first 2 hours of working on this project, I can generate a 3D model that at a glance tells me where I'm going to need perhaps some retaining walls throughout the project. I can come up with a pretty quick and clear idea of what typical sections I'm going to need and where. All right, it's fairly powerful in that respect. A roadway template, as I said, it's analogous to a typical section in many ways. It's applied to a corridor. A corridor, the terminology as it's used in MicroStation is identical to how it's used in transportation engineering. It's also what provides us our construction limits, and allows for multiple end conditions to match into existing terrain. You know, one of the other advantages is that intermittent design elements can be incorporated into a roadway template, into a single roadway template. And what I mean are things like curb, shoulder, sidewalk, depressed gutter, things that come and go. You know, and in certain, from station X to station Y, for example, sidewalk exists, and then after that it doesn't. I can include those into the template and then program the template so that at certain stations it will omit those and just draw maybe a turf buffer or a ditch section instead. Roadway templates, what they do is they provide us, they are the real workhorse of the 3D model. They provide us that initial pavement structure by allowing us to define that structure using points and connected edges. So here we've got, for example, a close-up of a PCC pavement and subbase. You see that all of the points are named, the center line, the right edge of pavement, which actually should be in this, the left edge of pavement for the way it's drawn. But every point, every critical point then is called out and named. And that's really important because the real power of a template is how we control how those points are located in three-dimensional space. How do I determine where that edge of pavement, for example, is with respect to the center line? And how we do that gets really interesting, but it provides us an awful lot of power. For example, let's look at a somewhat complex example. This again comes from the Route 2 job. Here we've got a widening along Illinois Route 2 for a small subdivision on the right, and you can see the road for that, the access road for that subdivision is also drawn, and that's actually existing alignment of Route 2. And we have a widening for a right turn lane, which you see at the bottom, which has, you know, a reverse curve taper, and then at the top we taper outward on a linear taper for the striped left turn lane. How can we take a single template and use it to generate a more complex narrowing and widening that we see going on here? Well, templates by default use the concept of fixed constraints. These fixed constraints say my edge of pavement is fixed at 12 feet from my center line or 24 feet from my center line and at 1.5% slope down or 2% slope down. Okay, those fixed constraints say no matter where you are, this is how the edge of pavement always tracks with the center line. So if I wanted to build this out, I could use a fixed template to handle the two lane highway approaching this widening, and maybe the 3-lane section in the center. But in between, I have to generate a separate transition, and that transition is linear only. So I could do a transition, say, for the widening for the left turn at the top, but I couldn't produce a transition for that reverse curve right turn lane down at the bottom. One other powerful thing that we can do with the template is we can use a parametric constraint. A parametric constraint allows us to use one template to do a linear transition. So instead of doing two separate templates, one for the 2-lane and one for the 3-lane part, I can say from station X to station Y, I want my edge of pavement to transition from 12 feet to 24 feet. Okay, I can specify a parameter called lane width and say station X to station Y, lane width changes from 12 to 24, and it'll produce a linear transition for me with one template. But if I want to get into curves, then I need to use things called horizontal feature constraints or point controls. And they're two separate things, but they accomplish the same thing. What these do is they allow us to provide a nonlinear transition for a point in a template like an edge of pavement by drawing a 2D line in our plan view. So if I draw, for example, a reverse curve in my 2D plan view, then I can tell my template, I say, okay, when you get to this station, I want the edge of pavement to follow that 2D line in the 2D plan view and just track with it wherever it goes. So if I wanted it to, you know, follow, you know, if I wanted to make a goofy sine wave or something along the edge of my road, I could do that. And it's a really powerful feature that allows us to handle really complex transitions. One of the other advantages to building highways using templates is it allows us to generate cross sections on demand immediately. Once I've built that 10-mile job using 2 or 3 templates, I can already start calling up cross sections. It's important to note the only thing that's going to be in those cross sections are the elements that are in my template. So in my picture, hey dummy, I don't see a curb and gutter or sidewalk on the left side of that road. Well, that's because they weren't in your template. But that initial ability to generate cross sections is fantastically useful, of course, for inspecting our how well our design meets our engineering policies and standards. The one problem with this at this point is that we can't generate sheet cross sections from this on-demand view. We still have to go through our traditional processes, which involves geopack. So if geopack is going to go away, something's going to have to happen to make that happen. And we're hoping it comes sooner than later. It's something we've begged Bentley for. When we talk about actually generating our alignment then, our actual model, like I said before, we use the concept of a corridor. A corridor has a single alignment. And throughout that entire corridor, we put in template drops. We take our templates and we have the template drop at specific intervals, 25 feet, 10 feet, 1 foot. It's identical to cross sections and their intervals. And obviously, the more drops you have, the shorter your interval, the more accurate your model is going to be. Unfortunately, it increases computational time and complexity. So when you begin modeling, you're going to want to keep your template drops to 25 feet and get things roughed in. Then as you get more and more detailed, you'll increase your template drops. In the top picture, you see the corridor represented by the pink lines. Those are the construction limits generated by the template. Those construction limits are only as accurate as the drop. So if my template drops were 25 feet, those construction limits wouldn't look the same. They'd look a lot different than they do in that picture. In that picture, I think they're probably, I'm guessing, maybe 10 feet or something like that. One of the other things that can happen is if you have multiple corridors. Remember, a single corridor has a single alignment. So if I have different alignments, they're different corridors and different templates. So if I have multiple corridors that overlap, you see in the lower picture is you have a side road intersecting with a main line. Sometimes the template generated from the side road can intersect the one in the main line. What we can do is we can clip one template against the other. I can clip that side road against the main line. And when I do that, that portion of the side road ditching that intersects the main line back slope goes away, and it looks smooth and it looks a lot better. So it's a powerful feature, but it's one that we want to use sparingly. The last type of template we can use are called existing templates. And existing templates are really good at generating 3D surfaces from existing survey data. In the picture you see here, if you're familiar again with the Byron area, this is a boat ramp along Route 2 as you head north out of Byron, just past the railroad overpass. That boat ramp is not a part of the project, so I used an existing template to follow the survey data points to map out that existing boat ramp surface. And I can recreate existing pavement, curb and gutter, sidewalk, turf, you name it, if I've got sufficiently good existing survey data. So now the only thing to do, for example, in this picture, is to take my proposed main line and my existing boat ramp and connect them with an intersection and entrance pavement. And I can very easily do that once I've got those templates built. The other element, we talked about, there's two parts to a design, to 3D engineering and design, and the other side of that, the other part is civil cells. And civil cells are where the real engineering happens. I probably shouldn't say that, but it's true. The real nitpicky engineering that we spend a lot of our time on happens on the stuff that is handled by civil cells. And what civil cells are modular cells that are used to create, for example, roadside appurtenances that you can't generate with a template. For example, the ADA ramp you see in front of you. And this is one of my own design, one that I did early on, trying to learn how civil cells work. Civil cells are modular in design. They allow us to build things like curb ramps, intersections, median islands, interstate ramps, roundabouts, you name it. And we can build fairly complex civil cells, but it's important to understand that they're finicky, very finicky. It is really right now the Achilles heel of 3D engineering for Bentley MicroStation. And I'm not really picking on Bentley to say that. I'm just saying it just is the major weakness right now. It's very difficult to learn, and the software is still kind of buggy as far as it goes. It's getting better, but it's not there yet. Civil cells are parametric. In other words, you can build the civil cell to fit, to accommodate our engineering practices. So if I want to make sure that my roundabout, I can generate my roundabout and change it by specifying a radius. Or adjust the reverse curve, a reverse curve approach to it, by specifying the radii of the reverse curve. I can do that, and it'll automatically update and regenerate for me. It's also customizable. Once I place the civil cell in a 3D model, I can do what's called dropping that civil cell, which reduces it to its base components, just like dropping a 2D complex line does. And then I can go in and I can customize and adjust those elements to fit whatever condition I may have in that civil cell. Oh, before I get to that, I want to show you, I want to show you a real life scenario where I have actually built something using civil cells. This again is the Illinois Route 2 job in the urban section in Byron. And I've recently released internally here at IDOT my first civil cell library, and it accommodates urban entrances. And in order to build this library, I picked a rather unique but tricky edge case. And what it is I have here a couple of urban entrances, and they have a continuous mailbox turnout that runs through both of them, as you can see, as well as a multi-use path that runs through their throats. And so I built my civil cell library using this edge case because I felt like it really represented most every kind of case that we might encounter, at least in an urban scenario. And you can see then on the right-hand side, there is the completed model, and we can pick it and focus in on it here. I gotta hit my key point snap. I'm not finding a line. But if we focus in on it here, you can see, that I have my my mailbox turnout with my tapered concrete curb and gutter. That's a 6-foot taper. It matches in nicely. Well, not so nicely there, but it does. You can make it match it in quite nicely with the curb and gutter. It just takes a little bit of extra care to do that. I have a turf buffer section which fits, follows the top of the back of the curb and matches to my multi-use path. And all of this consists of, I think, 4 or 5 different civil cells that I use to build that out. Now, once I've got everything in place, I can actually go in and I can adjust the civil cells to accommodate how things look. So, for example, you see the back of my urban entrance there. By default, it's 25 feet. I'm going to take a chance here and adjust it. This is pretty computationally heavy, and it's been known to crash computers, but we'll see if this works. But I can go in and I can pick certain lines in my civil cell, and I can adjust my entrance. There you go, it updated. According to these, in the sorts of ways that we traditionally do it now. So when I go out and lay out an entrance in a project right now, I want to work with it in terms of the apron length, in terms of the throat width, in terms of the throat length. I want to deal with it in those concepts, not in terms of edge lengths and vertices and things like that. And so by adding these specific control lines in the civil cell, I can go in and I can do that. And here, picking this yellow line here, I can adjust 1/2 of the width of my entrance. I have a mailbox turnout that's offset 6 feet. If I want to reduce the width, I can just pick this here, and that'll reduce the overall width of my turnout. So I can very quickly and easily go in and adjust and change this entrance to suit my needs. Now, once I've actually placed it, then I can go back and double check to make sure it actually fits our engineering policy. For example, you see this entrance, looks like the throat might be just a little bit steep. So what I can do, and again, this is an early design, so things aren't perfect, but I can pick a center line and I can view its profile. Take our chances here. Here we go. And there you see my centerline profile in the dotted blue. If you zoom in on it, you see, for example, here's my curb and gutter section. This would be the apron. This flat part here is the multi-use path. So my apron's at 1.5, my multi-use path at 1. And then you see my problem child, my slope there on the throat, which is terribly ugly. Now I can look at this and qualitatively right away say, oh man, something's got to change. I need to increase the slope on my apron. I need to lengthen my throat, whatever, but I got to do something. But if I want to know quantitatively what my slopes are, I can produce a report, and that report will quickly tell me what my exact slopes are. So you see here at the top, I see a -6%. That's the slope of my gutter. Down here is a 1%. That's the slope of my multi-use path. And then I look here and I see 33.42%. Yeah, it's not that I couldn't tell already, but yeah, we got a problem with that throat slope. So I can very quickly determine whether or not the design meets policy, and then I have all of the tools I need to make the adjustments to make it fit policy. And if I'm using a civil cell and I can't make it work the way I want it to, then we have a problem with the civil cell, because the idea here is that when we do 3D modeling, we do our engineering in 3D. We don't do this alongside our existing 2D processes, because if we do, it's not helping us. Either we do our engineering in 3D or it's no use to us. Okay, and that has been a key tenet, a key commitment to, in my mind, as I've gone through and developed these civil cell libraries, and so far it's paying off, and I think we can actually get it done. So moving back to our presentation, and I'm running out of time. Here's a quick picture of what those control lines look like, and we'll move on. Barriers. When we talk about barriers, what's standing in the way of actually making this happen for us at IDOT? Number one, first barrier is the software is buggy and slow. It just is. I'm not faulting Bentley for doing that. What they are doing is something phenomenal, actually. They're taking their existing 2D CAD software and they are back-ending a parametric modeling paradigm on top of it. That's hard. There's a lot of 3D parametric modelers out there. A good, if you want to play around with them, a good one is the open source FreeCAD project. I'm a contributor on that, so I can't help but hawk it a little bit. It's a fantastic parametric 3D modeler that is, in my mind, leagues above what Bentley is doing here, but that's only because Bentley is working, you know, with an existing software that was never meant to do this. So in time, they'll get better. They've already gotten a lot better than they have been even in the last year. I really think the software will mature, and it will become everything we need it to be. It's just going to take a little while yet. The other advantage and the other issue we're dealing with is old hardware. We're slowly overcoming that in IDOT. IDOT recently identified power users and gave us upgraded equipment to deal with this. I could talk more about those specifications of what that hardware looks like. But overall, though, most of our CAD staff still uses old hardware that really can't run the software. Letting schedules, big thing that's getting in our way. Why? Because we're trying to figure out 3D CAD and still get these projects to letting on time. It's not going to work that way. It's one of the issues we've run into that I can tell you from personal experience. It's simply not going to work that way. And so we're working through that and trying to figure out better ways to handle this and integrate 3D CAD without letting our letting schedules basically make that impossible. Obviously, we're short-staffed. We've been hiring people like crazy, and right now we're breaking even over the people we've lost. So we're short-staffed and we're struggling to overcome that. Training. It's a big issue. We need to train people. We need to have the material to train them on. You know, so we're really working to get that done too. And finally, we have an incomplete civil cell library. Bentley provided us 60 civil cells as a starter kit to get this done, and they're good, but we have a long way to go before we can really use them internally, and that's why I'm going to the trouble to build what I'm building. And right now I'm working on ADA ramps, and that's actually going pretty well. So the bottom line, in order to integrate 3D CAD, number one, everybody must use it. We can't afford to have siloed gurus, you know, in our organizations. Everybody needs to use it. Everybody needs to be an expert in it. And finally, we need to have our engineering done entirely in 3D, not alongside it. It doesn't make sense to do it any other way. So with that, that's all I had. Are there any questions?
Okay, sorry about that delay. I was actually researching the answer to the first question. The first question was, where do we find the handouts link? It should be right above where the questions bar is. There is now the PDF version and the PowerPoint version. So that was, where's the button to answer the slides. The next question, where's the handout area? Is there a time frame for implementation?
Initially, they targeted 2018. They really wanted to see, and I think that's still something they want to see, consultant projects submitting 3D CAD by 2018, but we don't have it ready to go. It's kind of hard to expect that from our consultants, and we recognize that. One of the other disadvantages, like I say, is we're short-staffed, and our central office, we've typically looked to them to provide the expertise and the training for our CAD services. they're looking at the district saying, we need you guys to step up. Now, District 9 and District 6 have done well to lead the charge, and they've actually got some stuff out. District 9 has actually led a few 3D CAD projects. District 2, we're among the more, further along. But really, this is sort of a district-by-district effort. So it could take 5 years, it could take 10 years. It could take a really long time, at least for some districts, to get on board with this. But all of us really want to make this happen as quickly as possible.
Okay, the next question is, where is a good place to find training?
Bentley's website has a lot of training, and if you talk to the Bentley folks, they can help you through that. There's the Bentley Learn server, for example, and there's like a question section. There's like a section that's focused on 3D CAD open roads, rather, that has a lot of links to valuable videos. iBug conference that happens twice a year, every year, is another great place to go to get introduced or get some advanced training on Bentley civil cells. IDOT, I know as we get more into it, we're going to do that. There's consultants out there like Envision CAD. I don't want to sell anyone, but they're the only one I know of who also provides training. So they're another great place to go. YouTube, you can Google YouTube, and I've seen stuff out there. There's not a lot, but I've seen stuff out there showing you how to do that sort of thing too.
Okay, the next question is, why did IDOT choose MicroStation if it is so buggy?
MicroStation took the lead in the transportation sector in the early 80s because AutoCAD just wasn't there. So they built transportation-specific tools, and as a result, they captured a lot of the transportation market by doing it. Nowadays, so, what are we going to do? We're going to go with MicroStation. I can't imagine transitioning or migrating to AutoCAD at this point. The hassle in that alone would be phenomenal. On top of that, while I know I seem kind of hard on MicroStation and open roads, the fact of the matter is they're doing something nobody has ever done before. And to be frank, if you go to Civil 3D, which is AutoCAD's equivalent, you're not going to be any further ahead of the game. And a lot of people say AutoCAD is actually harder to use than MicroStation. MicroStation actually handles data, for example, a lot better than AutoCAD. Their civil cell technology works better than AutoCAD's equivalent. So it might be buggy, but it's really the best that we have. And right now, we have to press forward with what we got. And I say that also knowing that it's getting better. And I want to be perfectly honest, it's a lot better now than it was even a year ago. I can do so much more without crashes and problems now than I could even a year ago. So it's just something we have to take in stride.
All right, another question that's along the same lines as before. Will IDOT offer training to consultants?
Eventually, yes. It's going to be something that we're just going to have to address. I don't know if there's any sort of training that's happened already, but I know that's something that's going to become an issue, become a thing eventually. I'm not the guy to answer the question, but I can talk to our people in Central and see if I can find something out.
I'm sure that this is something that ISPE would be very open to partnering with IDOT on, or bringing in some consultants. So perhaps we can chat with you and the central office about that for the coming future. The next question, will IDOT be exploring the concept of allowing Civil 3D submissions alongside Bentley MicroStation as some state DOTs have?
That's a good question. That's not something we've explored just because we're just trying to get our heads wrapped around what we're dealing with here with MicroStation. The legal issues alone of producing a 3D model in lieu of a paper set of plans has proved phenomenally difficult. So, but I imagine eventually there's going to be some convergence, between the technologies that makes porting between the two easier, or we'll say in the end, and and it might be right now that my first thought in this, and I don't know for a fact, but my first thought is look at the specification for what is required for construction for the 3D model. Because whatever's required for construction for the 3D model, the format may be agnostic. It may not care if it came from AutoCAD or from MicroStation. So at least as far as construction is concerned, I could see either source being acceptable. But in the end, we're going to want a 3D model that we can use in-house. And if we don't use AutoCAD, then we're going to need that MicroStation model. So I'm not entirely certain how to answer the question, but I'm going to say at this point, I wouldn't put a whole lot of hope in us accommodating AutoCAD Civil 3D anytime soon.
Okay. Is the implementation of this software in parallel with site ops, and will there be integration between the two?
I'm not sure what site ops are. Site operations. I'm not exactly sure what that means. I'm sure I could expand on it if I had a good definition of that.
Okay, if whoever asked that wants to add on, we'll get to it when we make it through. It says, you may have mentioned it, but why did you go away from Autodesk?
We never were with Autodesk. As I explained previously, Bentley's had the market in transportation, and we've been a Bentley shop. Well, I don't know, maybe we were Autodesk at one point, but as long as I've been here, we've been a Bentley shop. So it's really the only option for us in terms of where we're at and where we need to go.
Okay, there is a comment here that says add consultant budgets to the barriers.
Consultant budgets. Right. I've seen a consultant 3D model, and it's they've got a lot of, and it's no offense to our consultant partners, but they've got a long way to go too, and I can see it being a potential barrier. Yes.
Okay. Does IDOT plan on rolling out any tutorials for utility sewer 3D modeling design?
I built a series of tutorials for my urban entrances, and right now we're debugging them to make sure they're solid. And I don't see why we couldn't release those. If our internal civil cells get released, which again, I don't know why they wouldn't be. I think we release our 2D civil cells for consultants to use. It wouldn't make sense not to. So yeah, I imagine there's probably going to be stuff like that happens in conjunction with live training and things.
Okay. Here's a comment that it would seem that MicroStation will eclipse FreeCAD in this area very quickly.
Well, they're two different things. If you look at FreeCAD, FreeCAD is a parametric 3D modeler. The project's been around for 10 years, and it works with CNC milling and 3D printing, that sort of thing. I'm a contributor to that project because I'm interested in developing a transportation-specific element to it. It's really, really neat. It makes design alignments really fun. But yeah, it can't begin to do what MicroStation could do in a transportation-specific context. But when you talk about parametric modeling, FreeCAD is phenomenally better at it because it's natively a 3D parametric modeler. And Bentley has a long way to go before they have that level of intuitiveness, I think, and simplicity that FreeCAD has. But it's my opinion that everybody's got different thoughts on that.
All right. Will IDOT be looking to consultants to collaborate on developmental of civil cells?
We put out a contract with EnvisionCAD to have, or with Bentley, not EnvisionCAD, with Bentley to produce 60 civil cells for us. Will we employ consultants? Maybe. The question is who's got the expertise, and who's got the skill and the time. So that might be a valid thing. I can tell you right now, civil cell development is hard. If you want to build a quality civil cell that suits our needs, it's just hard. It took me, I think, 6 to 8 months before I had that entrance civil cell library well designed and well built. And it's still got problems, if you ask me.
Okay, another question. What types of projects will this be required on in the future?
Well, as I indicated initially, we're going to focus on reconstruction and new construction projects because those are the ones that benefit the most, preferably in areas where there's good GPS signal and good survey data. Internally, however, one of the things that we're exploring is simply doing 3D CAD for mill and fills. Why? Because they're super simple. And it's a great way for us to get our teeth cut on 3D CAD and get people familiar with how 3D CAD works. And I would hint any consultants interested in learning the ropes on 3D CAD, maybe start playing around with mill and fills and see what they can do with that, because there's good tutorials and it's something that you can teach somebody in a couple, 3 months time and actually produce a finished project.
Okay. Also, the Connect edition has been rolled out. Is there a plan for IDOT to leave the SS4 platform and adopt 3D tutorials for files for the Connect edition?
Connect has been a long time in coming. I'm at the IBOT conference that I went to. They showed us what the package is going to look like. It's going to be rolled out next year, and next year SS4 dies. That doesn't mean we're going to move to it, but SS4 dies. So yes, we're eventually going to have to upgrade. And what that Connect Edition is going to do is it's going to bring in any outstanding geopack features. It's going to take all of the existing Open Roads SS4 functionality. I think LumenRT, Bentley, I think, is trying to get their hands on auto turn, and if they do, or maybe they have, auto turn will become a part of that package as well, and everything will live inside one single package. So that's a good thing. But how quickly we're going to move to it, I'm not certain.
Okay, it says SiteOps is a 3D site design modeling software.
Oh, okay, so it's a site-specific software. Then I don't know. Without knowing more about it, I certainly can't comment on that. But I'm going to say here is that if SiteOps works with existing 3D models of specific formats, and we can accommodate those formats, and contractors like using SiteOps, then obviously, yes, we're going to have to make something work. But that's as much as I can say without knowing more.
Okay. How far away is IDOT from developing SUE/SUDA features?
As soon as they can get them done. SUSUDA is under development. I've played with it. I think it's really neat. I've learned how to do underground utilities using civil cells because SUSUDA just isn't there yet. But it's getting there. Maybe it's further along than I realize now. Really, for us, the only real limitation to it is making sure we have survey data. And our survey staff for the last few years has been incorporating I don't understand surveys well enough, but coding points and things to suit 3D modeling workflows. So as a part of that, then certainly SUSUDA needs will be met from our survey staff level. We just need to make sure that they're going out and they're capturing the additional utility inlet elevation data that we might need in addition to what they would normally get. And then of course the only thing left for that is making sure that our hydraulic staff and design engineering staff know how to also to make use of those tools.
Okay. I have, that was the last question. I have launched the quiz, I've launched the poll. So if you don't have anybody watching, feel free to skip it. Otherwise, if you could let me know how many in the range are watching with you. Thank you so much, Joel. I did put the PDF and the PowerPoint. I know a couple of you have said, or one of you have said, that you can't see the handout link. It should be right above the question bar. That was my delay, was running out to check another computer so I could make sure that I was seeing what you see. I will, if there's nothing else, I appreciate everybody's participation, and we look forward to you joining us hopefully next month, where we will have Lauren Milligan, who is a career specialist and HR specialist, talk about the art of negotiations, even in engineering. So thank you all so much, and have a great holiday weekend.
Thank you.